A 150,000 kilogram rocket is launched straight up. The rocket motor generates a thrust of 4 times 10 to the 6 newtons. What is the rocket's speed at a height of 500 meters? Ignore air resistance and any slight mass loss. So in this situation, we're looking at the rocket. The rocket is our object, and we're looking at what forces are acting on the rocket. Those forces are going to be doing work on the rocket as it moves. And then if we know the work that's being done on the rocket, we'll be able to find the rocket's speed as a change in kinetic energy that comes from that work being done. When we look at the forces acting on the rocket, we're going to have an upward force of thrust acting on it, pushing the rocket up. We are neglecting mass loss because we assume that there's a whole lot of fuel and it's only burned a slight fraction of that, covering 500 meters. We're ignoring air resistance, but if this rocket is taking off from Earth, it would still have gravity to deal with as well. So in this case, we have a free body diagram. We've identified the forces that are acting on the object, and we know that its displacement is 500 meters upwards, because it's, as it goes up in the air, that means it has an upward displacement to it. So when we want to look at the work done by the thrust is the magnitude of the thrust times the displacement in the y direction times the cosine of the angle between the two, which is 0, since the object, since the rocket is being pushed straight up and its displacement is straight up. Its displacement and the force of the thrust are aligned. In that case, the cosine of 0 is 1, and we can find that the work done by the thrust is 2 times 10 to the 9 joules. That's how much energy is being transferred to the rocket due to this thrust. But we also have work due to gravity. And that work due to gravity is the force of gravity times the displacement times the angle, the cosine of the angle between the two, which in this case is 180 degrees, since they're anti-parallel from each other. They're pointing along a line but in opposite directions. So in this case, the work due to gravity is 7.35 times 10 to the 8 joules, and that is a negative amount because gravity is pulling the rocket down. As the rocket tries to go up, gravity is taking energy away from the rocket. Our net force then is the net work is the sum of all of the works acting on our rocket. Note that the work from the thrust of the motor is greater than 0. It's making us go faster and upward. The work due to gravity is less than 0 because gravity is taking that energy away. And we see that the net work that's done here is 1.265 times 10 to the 9 joules. So this is the net amount of work that's done on our rocket by the forces acting on that rocket. This net work is energy being added to the system. That's energy being added to the rocket. The way that this energy is manifested is through a change in kinetic energy. And so we know there's a net amount of work being done, there's energy being added to the system. That's going to show up as a positive change in kinetic energy. Kinetic energy is getting larger because the object is going faster. In fact, this change in kinetic energy is the final velocity squared minus the initial velocity squared. And we know that initially we were on the launch pad, we're not moving at all, and so we can go ahead and neglect the initial term. And we can say that the work done is equal to the final kinetic energy of the system. That forces are applied, the object is accelerated, its velocity gets greater, and at the end it has a kinetic energy that reflects that amount of work that's done on it. This is the work, the net work that we found. That is equal to 1/2 times the mass of the rocket and from there we can find that the velocity of the rocket is thus. Given our significant figures, we can simplify to say the velocity at the end of this acceleration, this period of work being done, is 130 meters per second.